Hi there, this is Dr. John, your physics and math professor, and we're continuing our transformation series. We've looked at various different ways you can transform a function. Translation means, like in public transit, you're just moving, you're just being transported or translated from one location to the next without changing your shape, keeping you upright, keeping you in the same shape. That's what translations do. They move you left and right or up and down. Stretches and reflections can change your shape. Generally, you'll sort of look the same, but they'll be stretched this way, reflected this way or this way. And so we're going to look at a couple of examples of that. But what we're going to look at is problems that are the way that you're probably going to get them. I have two problems for you. I'm going to try to analyze them for you and show you how to set them all up and calculate the new values. So what we need to always do is start off by looking and seeing what is the base function here. Well, the base function over here is x squared. There's a lot of things that are being done. There's a 2 here, there's a 4 here, there's a 3 here, and you're trying to figure out how do we set this all up. Well, first of all, what we need to do is we need to deconvolute this. These are tied together. What we want to do is we want to have it so that we just simply have x minus 4 or something like that, and then we know that that's a shift to the left and the right, and then we want to have a stretch factor in front of it so that we know that that's a stretch factor. Then this is, of course, a vertical shift as well, or a translation. So let's try to deconvolute these. I'll do both these examples and hopefully that you'll see what I mean by that. So we want to have this just simply x plus or minus something. So we've got a minus 4 here. So how would we do that? Well, we'd want to take this 2 out of here. So let's do that. Let's go 2 and then x, and we'll want to have this. So if we go x minus 2, what would this be? This would be 2x minus 4. So this here would represent the same thing as this. Notice this is now the way that we like to see translations. Just simply a number, an x or a y, plus or minus a number, just like this, or a number at the end like this. So this is directly associated with the x, and this would be a stretch associated with the x. But this whole thing is still squared. Can't really tell from this one how much you shift or how much you stretch. Here it's much plainer. And one of the reasons for doing that is because what we're wanting to do is when we do stretches, we'll want to do the stretch first, reflections next. These two you can tie together. You can sort of look at the same thing. You can do the stretches and reflections and then the translations. It's very important to do that in that order, because what happens when you do a translation, let's just take a look here really quickly at a function, some sort of quadratic like that, and we were shifting it over to here. In this case, if we stretch around here, all the points here, this stays locked. We're stretching it like it's a stretchable surface this way. But if we shift it first, what do we stretch around? We would need to stretch around this new axis. But the calculations for that are extremely difficult. We have to find the distance that all of these things are from this axis and then stretch it and then label it. Very difficult to do. You could do it, it's just very difficult. So what we do is we first stretch, then translate the stretched shape. So we first stretch or reflect, then translate the stretched or reflect, because reflections are really just negative stretches. And so we do that first. So it's very important that we can separate these two. So once we've separated these two, we can act upon them. This is a stretch. This is a translation. We do this first, and then we're going to do this. And we still have a 3 at the end, plus 3. So let's take a look at a couple of points here. I'm going to give myself some space here, like this. Here's the original points, x squared. Well, the original points, of course, 0, 0. If we had to draw x squared, it would just simply be something like this. X squared, 0, 0 is on there. 1, 1 is on there. When x is 1, y is 1. Minus 1, 1 is on there. And then, of course, if this is 2, this is 4. 2, 4. I could take many points, an infinite number of points. I'm just picking a couple there, because you just need a couple. Remember, the shape is smooth. It's going to be changed a little bit, but it's going to stay smooth. So now I'm going to change colors here and say, how do we shift this? Well, what we're going to need to do here, because we want to do our stretch first, so we're going to do the stretch. This stretch is associated with the x. It's a stretch of 1/2 of the x value. So we're going to go take 1/2 of the x value, whatever that is, and then what is this going to do? And then we're going to have to add 2, because the x value is going to have to be bigger. So it's sort of the opposite of everything, in a sense. This is going to be a 1/2 stretch, and then we're going to add 2. Notice you'd get a different value if you went x plus 2 and then did 1/2. You're going to get a different value, so it's very important to do that in this order. And then I'm going to take a different one here for the y values altogether. So for the y values, there's nothing you're multiplying it by, but you're adding 3. So you're taking y plus 3. The first one here, 0, 0 times 0, just the x values, plus 2. So it's going to be 2. What would the y value be? You'd add 3. There you go. This one here, it's going to be 1/2 plus 2, so 2.5. And then the y value would be 4. This one is going to be minus 1/2 plus 2, which I believe is 1.5. And the y value is 4. All right, I have taken these points here, 0, 0, 1, 1, minus 1, 1, and minus 2, 4, and 2, 4. So that's the blue is the original here. This is the x squared. This is the x squared. And then I've taken this green here, and I've drawn this up here as well. So this point 0, 0 becomes the point 2, 3. Notice we shift to the right by 2, and there's really no stretch because we did the stretch first and it's right around this point. But this point here is a little more interesting. It starts off as 1, 1 right here, and it becomes 2.5, 4. So notice we squeezed this, and then we shifted it over. It's really tricky to do piece by piece. Much easier to do mathematically like this, all in one piece. Notice this graph here is squeezed a little bit from this original blue one. The green one is squeezed a little bit and shifted over. Shifted over to the right, squeezed this way, and shifted up by a factor of 3. Hope that helps with this one. I'm going to look at this one here a little bit as well. Give me 2 seconds to erase some things. All right, remember we talked about deconvoluting it, or pulling things apart. Here we have this is the function, sine. The original function, of course, is sine x. But then we've done some things in here. There's some sort of stretch factor here, or a squeeze factor. There's a shift. There's this, and there's this. So let's just peel them apart and see what happens. So we want this to be pulled apart. So we don't want it to be 2x minus pi. We want it to be just x, obviously minus something. So I want to take this 2 out. Let's take a 2 out. And then what would it be? X minus pi over 2. This times this gives you 2x. This times this gives you pi. So this is correct. This is the same as this thing in here. So this is going to be sine times all of this. And then we have this minus 1 in the front. And we have this 1 at the back here. So if something is inside the function like this, inside the function and tied directly to the x, it's related to the x. If it's outside the function like this one and this one, it's related to the y. So what we have here is we have a shift to the right in the x by pi over 2. We have a stretch or a squeeze of 1/2 in the x, because remember we're doing the opposite. And then we have these two things as well. So let's just write this up here. I'm going to write this over here so we have some space. What do we need to do first? This stretch. So first of all, we're going to have to take the x and multiply whatever x value there is by 1/2, and then shift it to the right. So this is the new x values. 1/2, shift it to the right by pi over 2. What are we going to do to the y values? It is a reflection or a stretch or a negative stretch in the y. So whatever y value we have, we're going to have to multiply that by minus 1, which is the reflection over the x-axis, or a negative stretch, and then we'll have to add 1. So this is the y value we're going to have, this is the new x value we're going to have, and then we're going to have the old x and y values. The old x and y values would be this here. It would be x and sine of x. So here I've drawn up this basic sine function and written out these couple of points on the original. This is the base function to this. So notice I've done 0, 0 right there, pi over 2 and 1, pi and 0, 3 pi over 2 and minus 1, and 2 pi and 0. You probably want to go through a cycle or go through the entire shape, try to find the extremes and graph those things. So I'm going to calculate these values here in blue and purple so they all stand out for you. So if I want to take the x value here times 1/2, which is still 0, plus pi over 2. So this is going to become pi over 2. The y value, will be still 0, and then it's going to be 1. So it's going to be like that. Those are the x and the y values there. So let's try this one. Pi over 2 times 1/2 is pi over 4. If we're going to add pi over 2, this will want to make a pi over 4. So it's going to be 2 pi over 4, like that. Adding those up will give me 3 pi over 4. 3 pi over 4. Just doing your basic math. I know we all struggle with it. And then this one over here, we take 1 times minus 1. We get minus 1 plus 1 is 0. So this one is 0. This one over here, pi times 1/2 is pi over 2, plus pi over 2 is just pi. That one's easy. This one is 0 times this is 0, this is just 1. And this one, 0 times this plus 1 is 1. There we go. So let's take a look at this point by point. The first one is pi over 2 and 1. So this here is pi over 2 right here, pi over 2 and 1. So that's a point right there. Maybe I should make that in this other color, big red circle there. And then this one is 3 pi over 4. That would be halfway between this and 0. So it's going to be right there, big red circle. And then here's pi and 1. Pi and 1 right there, big red circle. Then here 5 pi over 4. 5 pi over 4 would be, 4 pi over 4 would be pi. So it's just a little bit bigger than pi. So it's somewhere over here. And it's going to be 2. Like that. And then 3 pi over 2. This would be 2 pi over 2. This would be 4 pi over 2. So this would be 3 pi over 2. So it's right here somewhere. And that would be at 1. So we're right here. So there's a couple of our values. Let's see what happens if we try sketching it. We would start here. And since we're sort of flipped, we're going to go like this. This is the starting point here. We've flipped it. We've either reflected it this way or we've done some other kind of reflection. So we've done some sort of reflection. And you notice here, we've done a reflection in the y. So this function here is very hard to do by hand, but fairly easy to do, aside from using some of these fractions, fairly easy to do mathematically. I hope that helped. I'm going to do some more examples in the next video, so I will see you there. Bye-bye.